All right, good evening. Thank you for being here. My name is Fabrice Narandola. I'm director of CIRMMT. And it's a great pleasure to have tonight one of our new members at CIRMMT, Professor Suresh Krishna, who is an associate professor in the Physiology department, McGill, right? Right. And so, Suresh, as part of when we have new members coming to CIRMMT, new regular members, we ask them to give a seminar to introduce to the whole community of CIRMMT what their research is about and what they're interested in collaborating to trigger right away collaborations. And I'm very happy that we can have a few people in the room tonight, and we have people watching YouTube. And at the end of the presentation, and even during the presentation, if you have things that are not clear, you can ask questions directly to Professor Krishna. And then people who are on YouTube, you can use the chat function, and we have less, we'll be collecting questions and transmitting them so we can have something a bit more interactive. So, Suresh, you start.
Thank you. Thanks, Fabrice. Thanks for the introduction. Thanks for CIRMMT. Thanks for having me here. Yeah, it's good to see everybody back. I hear this is the first in-person talk in a while, like 1.5 years. So awesome. Okay, so the title for the talk is Listening, Seeing, Perceiving. This is sort of a whimsical collection of the kinds of things that I've done. So I'm going to be touching on multiple topics. Essentially, I'll try to stick to 3 topics and leave the others for later. So I'll kind of give broad overview of how I parcellate the world in my research work. Everyone parcellates it differently. So for me, it kind of fits into these 3 boxes. So there's the environment, which in my case is usually sound and light, but sometimes it can be touch, for example. And then that interfaces with our brain and our body, right? And then we have this paradigm where we believe that the mind is dependent on the brain body and interactions. And we have all the mental functions, perception, intention, planning, action, and so forth, attention, all your cognitive functions, mental functions. Now, one can, of course, essentially do your work completely like this. You can go from the environment to the mind, right? But having the brain in between, it's kind of the working hypothesis that putting the brain in between helps you make that connection a bit better. So a more precise diagram would have involved that, but mechanistically, we believe that it goes directly. So this is a kind of a working hypothesis for a neuroscientist, right? There are some out of the way hypotheses out there, which don't depend on the mind. And then I'm also interested in devices, algorithms, applications, so AI or robots or electronic music or any sort of kind of algorithm, right? And these, of course, interface with all 3. So you can use these to change the environment. You can have them directly influencing the mind. For example, if you're doing some kind of simulation or something, and of course, you have brain-machine interfaces as well. So the algorithm, what we learn about how this process happens, of course, influences how we think about devices, algorithms, and applications. So this is how I think about the sensory, motor, cognitive kinds of things that I'm interested in. Yeah. So the first, I'll talk about sound. So I'll spend 10 minutes talking about sound because after all, this is CIRMMT. I'll show something that should be incredibly boring to you, but it's just a way to get started. This is just a synthesizer, and it's a YouTube video from reverb.com showing amplitude modulation. So he's turning a few dials.
All I'm going to do is change the decay.
And this is purely amplitude modulation, right? He's changing the envelope of the amplitude. And you can hear some attack changes, sustained ADSR, right? So attack, decay, sustain, release. Okay. So this.
But now let's.
So and that's the topic I'm interested in. I'm talking about envelope modulations and looking at how the brain responds to envelope modulations. And of course, then we are interested in the phenomenology, the perceptual phenomenology related to amplitude modulations. Now, most of you are familiar with the missing fundamental, right? As musicians, most of the time when you hear a certain note, that note is not actually present in the spectrum. In most instruments, you hear the higher frequencies and you hear the missing fundamental from their periodicity. So for various reasons, psychophysicists, psychologists, and biologists use what is called sinusoidally amplitude modulated tones. So you take a pure tone and you change its amplitude in a sinusoidal manner, right? So you can change its frequency, you can change the depth of the modulation, you can change the carrier frequency. In this case, for example, it's 8,000 hertz, right? and it's going at 100 hertz. So you have the spectrum is very simple, which is why we use the sinusoidal amplitude modulated tone. It helps you do things mechanistically better because you only have this 3-band spectrum. It's like adding these 3 tones together. You might be familiar with the 2-tone phenomenon. That's the beating 2 tones. So this is a 3-tone stimulus. And in this particular case, at 100 hertz, usually you hear something that's called roughness. But that's not the only thing you hear. At very low frequencies, between 0 and 20 hertz, you hear something called flutter. Between about 10 to 75 to 150 hertz, you hear roughness. And then you will hear a periodicity pitch. So that's what I'm going to show now. It's a bit of a caveat. I hope that the periodicity pitch you hear is not from some distortion in my speakers, but we're going to trust that this is true periodicity pitch. I have to warn you that this sound is a little bit irritating to the ears, so steel yourself. It's a very high carrier frequency, so it's right. It's like a dog whistle. Okay, here goes. So you can see the spectrum change. That's flutter, and that's dissonance, roughness. If you hear the scale, and that's the periodicity pitch that came as the envelope frequency moved, right, as it changed. So what we're interested in is, we simply don't have a good theory of how the brain represents even this simple stimulus and how it decodes it across sound pressure levels and how we then perceive it, again, using this mind-brain dichotomy. So here's an example. So this is the auditory system. Sound enters the ear, hits the basilar membrane, hits this organ of Corti, right? And then it goes through an incredibly complex subcortical system, which is really, there are many, many nuclei. Even this is not complete. It must be skipping at least 10 different nuclei that are auditory. So it gets processed, and it gets processed really fast. So it gets to the auditory cortex by 10, 12 milliseconds after it appears at the ear, right? So it can be very fast appearance at the auditory cortex. So sound is one of our fastest senses. You hear and you respond extremely fast, right? Now, in the auditory nerve, which is the first station where sound is converted into brain activity, which is in the form of spikes, right? So you've got nerve fibers firing little spikes of action potentials. That's how we transmit the sound activity. From then on, it's neural activity, and that's how we interface with anything in the external world. So if you look at a simple 100 hertz stimulus, right, you've got this 3-band spectrum. And this is the filter that is seeing that 3-band spectrum. That's an auditory nerve fibers filter that is seeing those 3 stimuli. So in this case, it's well within the pass band, right? So you're going to see all 3. You're going to see the full amplitude modulation. At low frequencies, the spiking activity tends to occur towards the peaks, let's say the peaks of the cycle, right? But as you increase the frequency, it still fires at the peaks, but you will see that there's no real change in the total number of spikes fired per time in a unit time. Right? So if you count spikes, if you simply count how often the spikes occur, you will not be able to tell which frequency was being presented. Instead, in the auditory nerve, you pay attention to the timing of the spikes. So if it's a 1 hertz stimulus, it'll go brr, 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 like this. And if it's a 5 hertz stimulus, it'll go something like brr, 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 right? So, and that's each of these is one spike being fired by the auditory nerve fiber. So these are these spikes of action potential, which is how the nerves communicate in the brain. Now, in the cochlear nucleus as well, most of the neurons have this property that their timing carries the information, but the total number of spikes does not carry the information, right? So what we were interested in is this area called the inferior colliculus. The main point of the significance of this location is that almost all this complex subcortical activity gets integrated here. It's like a junction. And then it feeds upwards to the thalamus and then to the mass of cortical areas, right? So there's a lot of fMRI works with the cortex when you look at representation of pitch and so on and so forth. So the advantage of looking at the colliculus is that it's an almost obligatory relay for most of the subcortical activity that comes to the colliculus and then goes upwards. But if you look in the colliculus, essentially what we did, we looked in the colliculus and collected a whole bunch of data. Looking at the changes, responses of single neurons in a gerbil, which is an animal with very good low frequency hearing, right? So, and which is why we use it, because it has good low frequency hearing, so it's a good model for speech. Unlike say rats, which tend to not to hear low frequencies, gerbils live in caves. They are sensitive to very low footfalls, and so they have a good low frequency hearing because they have a big middle ear that helps them hear low frequencies. So when you have a stimulus like this, we changed everything: the carrier frequency, the depth of modulation, the modulation frequency, so on and so forth. And we characterized the responses of individual neurons in the inferior colliculus, recorded using thin electrodes inserted into the brain of the anesthetized animal. And the main point that I want to communicate, because I have other things to say, it's a large paper, but there's a whole bunch of, so what we're plotting here is the x-axis is the modulation frequency, right? It's how often, it's the periodicity, how often the amplitude is changing with time, right? In hertz. The y-axis is the number of spikes fired per unit time, right? And here you can see most of these neurons show what is called tuning. So if you count spikes, you can tell which was the period frequency that was being presented. And this is not present in the lower areas, auditory nerve and ventricle. So there is a transformation from a timing code to a number of spikes code. So once you're here, you don't have to worry about the timing. And this is useful because timing tends to get lost as you pass through the system. When you add noise, precise timing tends to get jittered, right? Especially at higher frequencies. So with each processing station, you tend to lose a little bit of timing. But if you convert it into a number of spikes code, that can get transmitted quite faithfully. So what we found is that we essentially have filters, if you want to call them that way, of spike rate that changes as the modulation frequency changes. And most of the neurons had some pattern that looked like this. So they either had that or that or that component. So very loosely, it looked like some weighted component of this. The important point that we noted was that most of these peaks lay below 100 hertz and a few more at 100 to 200 hertz. So beyond about 200 hertz, we found very, very few neurons showing spike rate changes that could be used to find periodicity, which means that the real range of periodicity pitch, right? The neural basis of this remains an open question. One can argue that it could be detecting spectral components. It's possible. Psychoacousticians have made models, but neurally, we still don't have a very good understanding because the spike rate peaks generally tend to occur below 200-300 hertz. So there was an existing model that claimed that you have a beautiful map that goes from 0 to 1000 hertz, nicely mapping pitch, just like you're mapping regular frequency, right? The whole brain is organized according to frequency for carriers. But for periodicity, turns out that we don't have the answer. And it was kind of a negative paper that said that, that model doesn't work. We do have spike rate changes that tell you. We have information possibly to tell what the periodicity is, but we don't have a fixed model that tells you exactly how it's being done because these filters, they are not stable with sound pressure level. So when you increase the loudness of the sound, often a neuron that's showing increases in firing rate at a particular frequency will start to show decreases in firing rate at that same frequency. So effectively, the filter changes. The filter is dynamic, and depending on the loudness, your filter can change. And that means that we do have a rather complex transformation into spike count, and yeah, we have work to do to understand what's happening in the brain when you go from. Okay, so summary. I just talked about this. This is still the most comprehensive data set, by the way, despite the time that has passed till now. And this is something that I really want to reactivate now that I'm here in McGill. I want to come back to my auditory roots. I've also done some work on auditory nerve responses to envelopes, modeling work. So this is also something I'm interested in, computational models of responses to sound stimuli, often in both psychoacoustic and nerve-based and brain-based, neuron-based. So yeah, that's another interest of mine that I'd be very happy to talk about more. Okay, so now I'm going to switch to, all right, that was good time. So I'm going to switch to vision now because this is how my career also sort of progressed. I wanted to switch to behaving a model. And then I got interested in vision, eye movements, faster movements, saccades. Does everyone know what a saccade is? A saccade is this, most of the time you're making these eye movements every 2 to 3 times every second. That's called a saccade. So you've got smooth pursuit, which is, if I'm following my stimulus slowly, and the eye is following slowly, that's pursuit. These fast, jerky movements that you make when you look like, those are saccades, right? So you got light now, and then you got the visual brain and the areas responsible for eye movements. And here we are interested in visual perception and attention, right? So I will kind of try to introduce the question here. So you got a crowded scene, right? So if I ask you to look at it, you have no idea what you're looking at, so you'll just look at it. Your eyes might be drawn to some salient features or some faces or something you might be interested in from your own personal, where you're coming from, your set and setting, your context, right? Whatever it is you're interested in. But if I tell you that, hey, my friend wearing a red t-shirt is somewhere in there, So very quickly, you will be able to look at the red places, right? Where we are able to very quickly select out the red locations, the locations on the screen that have red. It's effortless. This is how we function. So that means that we've got very powerful adaptive and dynamic filtering mechanisms for the visual scene. Something I'm interested in hearing as well, right, in terms of auditory attention, but I've not talked about that. So if I asked you to look at red, so I'm not marking everybody who has red. So these are the two that are red become salient, and presumably areas that don't have red, right, like they lose their salience, right? So one can hypothesize that these areas become enhanced in the brain, right? These areas become enhanced for you perceptually, and they are able to suppress the locations that you are not interested in temporarily, right? So you must have, if you have an attentional map of the scene, you must be suppressing the locations that you're not interested in. So it's a hypothesis for which we have psychophysical evidence because we have many behaviorally, we can show that stimuli presented at irrelevant locations are not seen very well. But what we didn't have evidence for was neuronal brain responses showing you very clear suppression when you're attending to other stimuli, right? Specifically, we predict that, each of these locations is represented in the brain because in the visual system, if you take any given area, a particular neuron responds to a particular part of the scene, right? And specifically to a particular part of the retina, which reflects a particular part of the scene. As the eyes move, what it represents moves with the eye, right? Because it's linked to the retina. So when the eye moves, you're now pointing in a different direction. You're representing a different part of the scene. But the neurons that are representing these two locations, right, or these two properties are suppressing. So if you make one location salient, it should suppress other locations. Next prediction would be, if I flash something at one of these suppressed locations, or even here, you should be able to see that temporarily you suppress here, right? So if you're looking for red, but if one of these people wearing white waves their hand like that, right? Even though you're looking for red, quickly or you look at someone who waved, and then your attraction will come back to the red stimulus. And this is distractibility. So you get distracted by something, and then your distraction comes back. How quickly your distraction goes back and forth, right? How quickly your attention shifts to a distractor and comes back can be looked at in individual differences and so on and so forth. So this is something that we are interested in. So while I'm talking to you, if suddenly something happens, I will look, and then I'll bring my attention back to you. How quickly I do that depends on how interesting that stimulus is, or how relevant that stimulus is, and how keen I am on coming back to my task at hand, right? And if making one location more rewarding should suppress other locations more. So by that I mean, if I'm really focused, right? If you tell me that I have to give this talk, there might be something coming from there, but if I look there, then the talk stops now, right? Then I won't look, even if something happens, because I am actively suppressing. So motivation is very relevant in terms of how you weight different areas. If you're completely unmotivated, you'll be distracted, right? This is also in lay language. This is what we say. When you're on task, when you're on focus, then you're on Zoom, you're attending, and then you screen out everything better. So we wanted to show all this in the brain, and that's what we did. This had not been done before, and we could show that every one of these predicted properties was true in an area that is supposedly involved in attention and eye movement in the macaque brain as well as the human brain, right? So our model now is the macaque monkey, which has a visual system and patterns of eye movements that are very similar to ours, which is the main reason to look at their brain. Their brain is also folded like ours, so there are many, many similarities with that model. So this is work that was done with Annegret Faulkner, who is now at Princeton as an assistant professor, and Mickey Goldberg. It's a bunch of papers. So yeah, that's the point that I want to show you, physiological mechanisms for attentional filtering. We have animals. We train them to perform these kinds of very complex tasks while looking at a monitor and indicate responses. And we use a very, very thin electrode. So once the electrode entering the brain is not perceived by the animal or by us. During epilepsy surgery, awake humans have electrodes inserted into the head, and it's not perceived negatively. The brain itself does not have any pain receptors. So we insert these very thin electrodes, and we of course also track the eyes in macaques who are performing tasks like playing video games, essentially, sort of their video game. Yeah. And There's a bunch of visual areas. So there's the frontal eye field, parietal cortex. The back of the brain is where the visual signals first come to the cortex. V1, V2, V4, there's MT. We are recorded from here. So this is actually a famous map. As you can see, there's a lot of complexity. We are picking one area, but we are far, far away from getting any sense of the complexity here. So we look from there, which is in the parietal cortex. And yeah, these were our predictions, right? And so we did an experiment where we had the animal fixate at the center of a screen. Now, all these stimuli were not presented, only one of them was at a time. And then we wanted to test the hypothesis that making one location more relevant should suppress other locations. So we had the animal plan an eye movement to say one spot over there, right? And then we flashed a stimulus at the same point on the visual field. Let's say the neuron, the stimulus was flashed over here, while the animal planned movements to each of these other locations, right? So the flash will always appear here. The animal plans eye movements to different locations on each trial, right? And what we found was the blue is the situation when the animal is just fixating. And that is the response to the flash distractor. So you got an immediate response. That is, neurons there start emitting spikes when something is flashed in their receptive field. And so this is a response to something happening outside. It's like a click response. You click and then you immediately get a click response, right? So in this case, you have a flash and you have a flash response. However, if you're attending to, say, some zone of these spots, that flash response is suppressed, which is essentially what we wanted to show. That is, if you're actively attending to something, then your response to a flash distractor is suppressed. And you don't look towards the distractor. And the animals never do, because if they look towards the distractor, they lose the trial. They lose the juice that they get on that trial. So they're doing these trials for juice reward. So what they're doing is they're planning an eye movement when something flashes. They ignore the flash successfully, and the brain also shows a suppressed response to the flash. And so we are showing this correlation. Next, we showed that the flash also suppresses the response, right? So it's a competition between the two. So we record from there. So when you're planning an eye movement to a particular location, that area is represented by a substantial increase of firing to that. So right, if I'm planning an eye movement to this location, neurons representing that location will be firing very fast. That's how it's a very strong response. But that flash over here briefly suppresses that activity, and then it comes back within about 300 milliseconds, your attended location. That is like a distraction response. You're attending to something flashes, you briefly attend to something, and then you bring your attention back, and your activity comes back to normal, right? And I said something about reward. So if you do the same task with two different rewards, right? If you do it under a small reward versus a large reward, you see that the distractor response is lower when you have a large reward, right? That's because when you have a large reward, you're more motivated, you're suppressing distractors more, and your brain response to the distractor is less, right? And similarly, when you're doing a task for large reward, the eye movement planning response is larger than when you're doing it for a small reward. So you're very sensitive, and the brain is also showing exactly that sensitivity. And finally, and this is quite important, we actually find that it's relevant to behavior. So when you make a mistake, that is when you look towards the distractor response is actually larger on those trials. And when you make a mistake and you look towards a distractor, the target response is weaker on those trials, right? So the brain activity is correlated with what you're going to do. On trials, when you break the fixation and look towards the distractor, you're actually paying less attention and your activity is lower. And your distractor response, the thing that caused the distraction, is higher, right? So what we are looking at is essentially competition between your relevant target and your distractor. And it's easy to translate that to an auditory situation. You're listening to speech, there's something that happens, you pay attention and you come back. The distraction may not always be irrelevant. It could be a cocktail party effect, like someone is saying your speech and then you're filtering it at a certain level, then you pay attention to that, and then you may stay attending there because it's actually a relevant distractor. So not all distractors are irrelevant, right? Okay. So recap, we found an area and we show that where the representation shows the competitive long-range suppression that is expected from an attentional priority map, okay? So I'm going to skip to have one more story here, and I think I'm doing well on time. So we'll take a little break if anyone has any questions or if you're totally lost or no, everything is okay. All right, yes, go ahead.
About this filtering that our brain is doing both, I think it's both on listening and
Yep.
looking. I guess it changes between individuals. individual.
Yep.
It also can change during time if there is
Yep.
changes also, I mean,
Yep.
with the training.
Absolutely.
Okay.
Absolutely. Yes to all of this. You can also learn to filter known things. So if it's a repeated distractor in the same place, or if it's a repeated feature, so you kind of know it, then you will learn to be able to filter it better because the surprise is lower, unexpected stimuli will be larger. Reward obviously changed it, right? That's motivation. And yes, absolutely, when you're more tired, then you're distracted, more distractible than when you're not, and so on and so forth. Yeah. Yeah. Okay.
I'm thinking of, well, reward. I mean, for them, maybe it's kind of easy to find what is the right word, but
Correct.
a performance situation or for training performers. Yeah, what kind of reward except for their self-satisfaction?
Yeah.
I guess that's
Reward and punishment, though, right? So normally it's reward and punishment, right? Especially in a performance situation.
But I guess could you give a feedback right away, kind of based on these type of measurements?
Yeah. In principle, you could, but I think in real life, you would have invasive issues. Nobody would consent to have being monitored that to that level, right? It's that's very too invasive. But no, that's an open question, actually. Can you actually be trained to be motivated? I think it's almost certainly true, because if you're in changing the motivation level, then this would change the I actually had a picture somewhere there of a concert in Ephesus in Turkey of the Vienna Chamber Orchestra was playing, and then a dog walked in. There's this famous YouTube video, and the dog came in and sat, and you can see the different performers, how they react. Some are like, the music is going on, and for my lay ears, it's going smoothly. Maybe good ears can hear mistakes, but they were playing, and some are like dead focus, while others are able to watch and keep playing, So there's a certain element of how much attention they pay to that dog when they're playing this piece. Okay. All right. So now what I want to talk about is attention shifts across eye movements. And by this, I mean, so let's take this mother monkey, right? It's a baby monkey who's sitting on a ledge. So it's a kind of precarious place. So the mother monkey is looking around. It's not spending all the time watching the baby, right? So looking around, but it's kind of through the corner of the eye. It has some attention on the baby. So that, if the baby slips, it knows how to catch it. And there's something like we all do. We're multitasking, right? You know something is important, but you're not looking at it all the time. Okay. Now, this raises, say, certain issue. So this is a bunch of papers which work with Tao and Stefan. So the reason it raises an issue is because when you're looking here, the baby monkey's image falls on this point on the retina, right? The retina is the back of the eye where the neurons are, which respond to light, which convert light into those spiking events that I talked about in the optic nerve. So it falls on that point A. But when the eye moves, the baby monkey's image now falls on point B, right? So it's actually different neurons before and after every eye movement. Different neurons are responding to the same image because neurons move with the eye as what they represent, right? So the neurons are representing location A will respond to the baby monkey before the saccade. Neurons are responding to position B, baby monkey after the saccade. So what we have is a situation where around the saccade, you should be attending to neurons A before the eye movement and attending to neurons B after the eye movement. And ideally, you should do it in time with the saccade, right? Your enhancement of the activity, right, that I showed you before. If you're attending to planning an eye movement to something, those neurons have higher activity. That enhancement should occur to neurons representing A until right before the saccade, because otherwise you'll miss something that the baby monkey does in the time before the saccade, right? And after the saccade, very quickly, you should be looking at B. You should be attending to B, because otherwise you'll miss something that the baby monkey does after the saccade, right? So you got to switch. Every time you move your eyes, inside in the brain, a certain searchlight kind of thing has to switch from A to B, right? That's a simple model that I'm using. So we use a human experiment, and this kind of gives you the flavor of how we convert these natural tasks. So we have a spot that fixate, and then you have these 4 moving dots, right? One of these is the target. This is the baby monkey, effectively. That moving pattern has a very brief change. I think it's 2 frames, so it's about 26 milliseconds or something of jitter, of speed, right? And then it continues to move in the same direction. So you cannot see it unless you're really attending and looking for it. So what happens is this fixation point jumps, right? And we are looking at how well you detect that jitter around the time of the eye movement. So what we found that in humans, and this is almost every human, it was very uniform, very, very quickly after the saccade ended, after the eye movement ended, that's within 30 milliseconds after the eye movement ended, you're able to pick up the changes again, the jitter. So that means that it looks like attention is shifting almost in time. And this is why we use the monkey. So we switched to the monkey, did exactly the same task, and they learn it quite well. And we recorded from an area called MT, which is very, very responsive to visual motion, has very clear receptive fields. So, right, you know whether it's the baby monkey, which, when the eye moves, it no longer represents the baby monkey. So there's a population of neurons that's representing the baby monkey before the saccade, population of neurons that is representing the baby monkey after the saccade. So what we want to see is how the activity enhancement moves from this population to that population right around the time of the saccade, right? And that's what we did. So what you see here is this increase in activity that you see. This is the number of spikes again. We're counting spikes. This is the increase in activity. This is the neurons that are representing the baby monkey before the saccade, right? Effectively the target. And immediately after the saccade, you see that the activity, there's no difference anymore. So the attentional effect has gone to zero. So the attentional effect switches from the population that's representing the target before the saccade to the target that's representing the population after the saccade. And this switch happens, this zero here is the time when the eye movement ends. Its switch happens almost very, very well timed to the eye movement itself. And you see this enhancement occurring in the correct population within 30 milliseconds of the saccade ending. So it's a very, very nicely synchronized shift of attention along with the eye movement. So recap, attention shifts are fast and saccade synchronized, and this helps maintain spatial attention on relevant stimuli so that they can be optimally tracked and processed across saccades. And this is especially relevant when you're tracking, right? When you're tracking, you make an eye movement, the stimulus is moved, you predictively know where it's going to be, you make an eye movement to catch up, and then you can move, look at something else, and all these transformations happen on the fly. And it's not just we who just do that, bees do it, like birds do it, and with very few neurons even. So this is a very well conserved thing. Keeping track of certain objects while you're flying, it's an important and relevant feature. Okay. I just wanted to say that I am very interested in eye tracking and scanpaths. Many of you might be familiar with this picture. I don't know if, okay. So this picture is the unexpected visitor, and Yarbus put suction cups on the eye in the 1960s to see and measure eye movements. He didn't have infrared eye trackers then, but he did some very nice work. So what he showed was that this is what you see, what you look at when you're not told what to do. So you're just looking at the scene and you end up looking at faces. That's what we normally do. When you don't have anything to look at, you start looking at people's faces, right? But if you're told to estimate, I think in this case you're told to estimate how rich they are, estimate the material circumstances of this family, then you end up looking at their clothes, you end up looking at what they own, and etc. So that's where your eyes move, and you don't look at the faces so much anymore because there's no information. He tried a bunch of other tasks as well and showed that what you look at depends on what you're looking for. Like every other phenomenon nowadays, when you repeat these tasks, there's some evidence that the effects are not so strong, but there's no doubt that they exist. We can track the eyes to get an indication into the mind. This is the basic idea. Right? So I'm very interested in eye tracking from many different respects. One thing I've done is I've looked at transfer of information, not just the attentional information that I showed you, but also just content information across sequences of saccades, which are kind of models of reading. So you see the scene, you kind of get a picture, you gist, and then you move your eye, right? Every time you move your eye, you have to be carrying over information, allocating tags. So you see, I see something briefly, I didn't get all the information about it, look away, I make a choice of where to look next. There's still some information to be gained there. So then I look towards it, right? And I'm carrying over the information I gained in the first brief glance to the time when I looked at it. So it's each eye movement is not a new look at the scene. You're carrying over information and building up information until at some point you get bored and say, okay, I'm done. I got what I wanted, until the scene changes or your needs change, for example. So also interested in interaction between visual and auditory intention shifts and eye movements and how these connect. And in particular, I'm very, very interested in the fovea. So the fovea is the central part of the retina where you have the highest sensitivity, pretty narrow field. This is why we move our eyes, in order to position stimuli onto the fovea so that you can see better. And the reason to move your eye is to bring the locations of interest to have them fall onto the fovea so that you see them better. So you might have heard of AMD, acute macular degeneration. Generally, you have a central hole, so your fovea areas get affected, which is why it's very bad. in terms of reading and other daily functions. Glaucoma tends to affect the periphery, for example, but fovea, the AMD affects the fovea. Okay, so I'm very interested in the fovea because for various reasons, we don't know very much about foveal attention and how the fovea processes. There's technical reasons because tracking the eye to very, very small movements, the fovea is very rich in neurons. So the smallest eye movement will cause us effects that you need to monitor. So if you're not tracking the eye really, really precisely, you're not able to do foveal experiments very well. And this is the technical reason why we don't pay attention as much to the fovea as we should. So I'm very interested in sort of improving eye tracking measures, making them, and working, with the geometry and optics of eye tracking and trying to track the fovea. So this is something I'm very interested in. Okay. Finally, actually, yeah, it's pretty good. In terms of collaborations, I'm open to. I'm coming to hearing. I'm like excited, right? After many years, I'm coming back to hearing. It's just fun to be back in this domain again. There's so many ideas that were put on hold in a notebook, that was closed. And I'm happy to open that notebook. There's tons of things I'm interested in: envelope processing, pitch processing, and it's great to work in applied domains. So as musicians, for me, the crosstalk between the two is very interesting because the things that very well that and vice versa. So this could be there's a lot of opportunity. So I'm very interested in auditory processing, especially envelope modeling, responses to envelopes, how to predict responses to arbitrary sounds by looking at classical envelopes, for example. Particularly interested in auditory attention expectancy predictions. So this is something that in music, we play with this a lot. There's all these ongoing research about what makes something interesting. A little bit of surprise seems to be the answer. Shouldn't be too surprising, right? You should be able to predict it, but it shouldn't be completely predictable, right? And of course, this may depend on whether it's pop or whether it's classical or whether it's jazz and so on and so forth. So that playing with that expectancy, that sense of beauty when you listen to something. And of course, there is something that is surprising, but then you know it. So just being able to predict what's coming next actually helps sometimes in your enjoyment. So it's a mix of this, right? So it's both unpredictability and predictability. And these are the sort of conversations that I'm very eager to have. And also, are there natural tendencies for predictions, right? If you see a scale going a certain way, depending on what you're exposed to, where do you expect the note to land? And so for me, coming from an Indian background, getting Western scales in my head has always been difficult, especially when they go atonal. It just sounds wrong. And just like that, exactly the same. I don't remember who it was. A very famous composer said he could understand Indian music analytically, but he just couldn't. It didn't feel right. Everything was falling in the wrong place. And yet the systems are not that different. They're actually small changes in style, and it causes a very large effect in expectation. So I'm interested in eye tracking, audiovisual phenomena, and I'm particularly interested in mind-brain technology interface. So instruments, devices, electronic music, open source eye trackers, so on and so forth. Okay, I hope that gave you a certain flavor of the sort of things I do, which was my goal, and hope it was not too dense, but just at the right level of interest. Not too boring, not too unpredictable. Okay, thanks.
Thank you very much. Yeah. Thank you. Do you have questions? You have questions, Les, over there?
There's one. Yeah.
Okay.
So far.
Get started.
So someone asked, I think it was at the beginning of the presentation when you were talking about sound synthesis and stuff. Someone asked, have you any insights that might have practical application for composers and or mixing engineers working primarily with synthesized sound?
Not off the top of my head, but I hope to answer that better in 2 years with the help of the various people and collaborations I make at CIRMMT over the next 2 years. That's my answer to that. Yeah, I would really like to be able to give a positive answer to this.
I have a couple of questions.
Yeah, go ahead.
That's fascinating. I will start with the first one. When you were speaking about neurons, when it's about visual capacities, basically there's a map between the neurons that are capturing the light and then transmitting to the brain. That's kind of a function of the location. But when you were speaking about the audio part, and then you see the spikes, and then there's not the same kind of thing, or I didn't understand very well. you don't have neurons that are speaking about pitch and some about time, and so how does it work? Because it seems like the spikes are grouped together, they give some information, but it's hard to predict. So
Absolutely. So in the in vision, oh, that's the dog, by the way. Anyway, no, absolutely. So in vision, the one second, let me get this back. Yeah. So in almost until most areas of the auditory cortex, the organizing principle is frequency. So if you take a pure tone, right, and look at the auditory nerve, and this here is actually an example of that. This nerve fiber will respond to a pure tone that falls within its band. It could be somewhere between, say, 3 to 8 kilohertz. When you present a pure tone, a tuning fork, right? Pure tone, 3 to 8 kilohertz, it will respond. If you present noise, if the noise has components between 3 to 8 kilohertz, this nerve fiber will fire spikes. If you present band stop stimulus, right? You take a stimulus, you filter out everything that goes from 3 to 8. This neuron will be silent. This nerve fiber will be silent. Nerve fiber being the auditory nerve, and also almost every area along here. Frequency is the organizing principle. And this is absolutely true. To read off frequency from the map, we kind of know the code. There are many details that are missing. So the topographic organization, and also, let's say the inferior colliculus. If you go in different locations along the colliculus, they will respond to different frequencies. And there's a very systematic spatial organization. So if you go to one location, you find that frequency, all the neurons nearby will be responding to that band. And when you move from there, they will respond to a different band. And it's very predictable. What we don't know is the orthogonal organization. What about periodicity? If I fix the stimulus, right, to this frequency zone, all three are well within the neuron's band. I'm just changing the location of the side bands very slightly, 100, 200, 300. It's not much because the filter is very wide. But the neuron will respond very differently to these small differences. So this is the debate in psychoacoustics between spectral cues and temporal cues. So for small variations like this, you don't think that you're relying on spectral cues. Rather, it's the temporal envelope cue that matters. And the envelope cue is what I'm plotting here. So for example, the difference between these two is just 4 hertz. So these two bands are just moving 4 hertz away. So there's not enough information in this filter's output magnitude to tell you that you're moved away 4 hertz. But you can tell from the temporal domain because it's changing dramatically. Something is clicking at 4 hertz, 6 hertz versus something is going at 2 hertz, right? So periodicity, how is that represented? So if I have the frequency, I know that a bunch of neurons are responding to this complex. But when I change the periodicity, are different neurons responding? We clearly saw that they are. But is that an organizing principle? Is there topographical organization? I mean, those are the open questions. So the equivalent of space in the auditory system is frequency. And you can think of that as position along the basilar membrane. Because the basilar membrane, we know from Helmholtz, if you unroll it, then different points on the membrane respond better to different frequencies. So just like the retina represents 2D space, frequency is representation of 1D space, one-dimensional space along the basilar membrane. Is that making sense? Every neuron is responding a particular point on the basilar membrane. You can think of it like that.
So, I mean, I just want to make sure that I understood. The answer is basically by having, I mean, I have not understood that. By having more than one tone at the same time, you create the periodicity, and that's what the brain will kind of recognize differently. Well, they will recognize the tempo of the frequency, the periodicity.
That's right.
Otherwise, they would not get the difference because the frequency map, let's say, is not sensitive enough.
That's right. That's exactly right. And this was also exactly. So psychophysicists have also made calculations. So you have your passband of your equivalent rectangular bandwidth. You can tell how much you've moved. And that is not enough. If you take a single tone and move it, it may be less than your just noticeable difference for that note. But you can detect it when you have 2 of them, because now you have the cue that the envelope flutter has changed. So you can do it by using temporal cues. That's exactly the point. Yeah.
I hadn't understood it before. I have another question because when you gave the example about the sound, maybe I'm getting old, but I don't think I was able to see,
Yeah.
to not see, to
Here.
hear until the kind of the end it became kind of
Yeah.
more clear. Would you mind
Playing it again? Yeah, sure. If you want to hear, that thing is sensitive ears, right? One second. One sec. What I will do is I will increase the volume of my computer. So it's going to get worse. Not too much, just a little bit. You can close your ears. Yeah. I don't know whether I can pause it, but what you will see here is what you will hear is what you could do is you could watch. Don't ignore that completely. Just watch this, right? What's happening is this component, this component remains the same. These two components are going to move up and move down, and that is your modulation frequency. Right? I'm not showing you when it's at 1 hertz because it'll really be superimposed. From 100 hertz onwards, I have a label. But what's happening is that those two components are moving, and the rate at which the amplitude is changing is simply that 100 hertz here, or 2 hertz, or 4 hertz. From 0 to 20 hertz, you can follow each modulation. So you hear it as flutter. That's like flutter. And then from around 20 to 100 is dissonance. That's roughness that musicians use to in their music to create that sense, right? So that is dissonance, where you have anything between 20 hertz to about 150 hertz or so. You can hear roughness between your tones. From 150 on, you actually start to hear the periodicity pitch, which is how instruments work, right? You've got 600, 700, 800, 900 producing a 100 hertz note, which is why the timbre changes for different instruments. So now that's what you'll see. I'm going from low frequency to high frequency. So this is 8,000. It's all flutter. It's roughness now, starting to get rough. And now the pitch. And that's your periodicity pitch. And again, the caveat is, I'm not sure that this is not the part of it is not a distortion product, which is F2 minus F1. But let's say that that's the pitch. Okay. Yeah.
Just from the chat, a bunch of people congratulating you on a great talk, saying thank you.
Thank you for attending. Yeah.
I have more questions.
Yes.
Now I'm switching to the visual domain.
Yes.
And of course, well, I'm a musician,
Yes.
percussionist, playing at the back of the orchestra, and I have to look at my triangle at my school, and at the corner there, at the conductor, I'm trying to look at the conductor sometimes. The first violin, to make sure that they actually align. Extra. So basically, we use a lot of our peripheral vision.
That's right.
And so, I did some research on development and high hand synchronization. And right now, with the systems we have, it's kind of like for eye tracking, it's difficult to detect peripheral vision or how we use it, or and I don't know if there are ways to do it better. And I'm wondering when you're looking at it from the neural perspective, how does that translate? Because you were trying to get the fovea at the right spot, because that's where we have the most accuracy and most information. But then in the meantime, we use other spots. How does it translate? How can you see that?
Yeah. So I might surprise you a bit here by turning it around. The point that I was making towards the end is that all of the recordings, everything that is it's actually from the peripheral vision, because we simply get the animal to fixate, and then they ask them to attend peripherally. Why don't we ask them to attend centrally, even though that's what's interest? That's what I was saying. We are not confident enough in our ability to detect very, very small changes. Once you come to the central fovea, neurons are representing locations on the field which are maybe 1 degree in diameter, maybe even less. So the smallest eye movement will take the stimulus in and out of the location that it's looking at. Once you're in the periphery, neurons it's coarse vision. We don't see that well. That's also why we don't see very well in the periphery. The receptive fields are big. Each neuron is responding to something that happens roughly there. It's basically functioning, for example, that you're looking here, those neurons are very sensitive to movement. So you're looking at somewhere, moving things are interesting. You quickly turn your head and you localize it extremely well. For this, the neurons are good. What happened there? You don't know until you actually turn your eyes to that location. So you don't have sufficient resolution to know what happened. In our tasks, we have the monkey fixate, or humans fixate and do a peripheral task. So we are do something very hard for them. They have to keep their eyes fixed and kind of look out of the corner of their eye to do peripheral attentional tasks. And most of the time when people talk about attention in human psychophysics, they're actually talking about peripheral vision. They're actually talking about what we are able to see from the periphery. And that's kind of counterintuitive, but the reason for this is because we are not ready to do things at the center. The center is where we are really making fine judgments. So if you're threading a needle, your attention is shifting to a lot of different points right around that needle. You're looking at the point of the thread, you're looking at the hole, but we don't have it's not easy to have the resolution and do the experiments where you're making all these. So it's starting. People are starting to build stories around it. This is something I'm interested in. But actually, so the attentional talk that I gave is essentially more about peripheral vision. So we make our stimuli sufficiently big and sufficiently clear that the task they are doing, we try to get them to 75% correct, which means we adjust the size of the stimuli so that they are able to do it. So we will not have them do a task where they are fixating and in the periphery and some very, very thin vernier acuity task is being presented. No, that makes no sense because they would simply not be able to do the task. That's so. And for detecting things in the periphery, small eye movements are not a problem because you're making small eye, right? The field is moving a little bit, but it's all within the zone that you're representing. So that neuron is roughly representing this whole region. So when you make a small eye movement, it's still within that neuron's range of representation. So we are absolutely fine technically to keep recording from the neuron, while also we can detect the small eye movements. So the issue with eye movement detection is it's not that we can't detect small movements. We are not very sure of within that central 1 degree where exactly you're looking. Because the way we calibrate an eye tracker is you fixate and you say, look straight. But even there, your eye is moving. So the calibration itself sort of assumes that you're looking straight. So I cannot tell you exactly where it's falling on the retina, but I can tell you that there's a small movement because the new high-powered iLink, for example, has excellent resolution in detecting small movements. So you can tell that there was a microsaccade. What you can't tell is from where to where the microsaccade happened. You cannot be sure. That's the issue. Does that kind of answer the question? So.
I have another question now.
Yeah.
Because you did talk to us more about the auditory and then the visual.
Yeah.
Now musicians, they use really both.
Yeah.
And are you able to measure them both and look at both the suppression and the focus? Because in fact, we are constantly suppressing some information. So we are putting our attention on the right thing. And that happens both auditory on the auditory and visual.
Yeah.
I mean, it's like, so that's even more complex.
Yeah.
So
Yeah.
is that possible to?
Absolutely. So cross-modal attention is a big field. It's quite open, actually. I mean, how you switch attention between vision and hearing. What is really interesting is in real life circumstances, how is attention switching under where? I'm sure it's very dynamic. Nobody stays all the time, pinpoint focus. You're also, you should not be. Exactly, right? So you kind of plan a certain sequence and exactly how practiced it is, right? That would make a difference. If you're playing something extremely practiced, you say, I can play it with my eyes closed, right? That's a kind of a misnomer because actually you mean you can play it with your eyes open. But okay, you know what I mean, right? Eyes closed, you don't have to read the score. I guess that's what it means. But and also how you switch your attention and where you're looking and at what point strategically do you decide to pay attention, which tells you which part you consider more difficult or which parts you consider more relevant, right? In games like baseball or cricket, which have these face a ball, then take a break, face a ball. The professional sportsman will always say the thing they learn to do is switch on and off. So when you're ready to face the pitch, you're on. But anybody who stays on all the time, it's very hard. So what you do is you take a break, and then you think about something like, what should I eat tonight for dinner or something? Then come back. And this way you can sustain it for a very long time. So this kind of on-off thing that people often do. In the context of a performance or a dance performance, it's very interesting to see how attention drifts. And while you're, of course, keeping track of so many things, right? Timing, small timing, longer timing, just strategizing, getting ready over time. You know the piece, so you know when you're going to be called upon again. If you're playing something that's not relevant, okay. Where your role is not so important, like so those people who have to hit the gong once or something, then you know. So you just you take your time and you do other things. So yes, absolutely. So how you switch under different time scales, long time scale, medium time scale, short time scale, absolutely open, and how that there's so many applications. And again, one is cautious because when you deal with actual people, there's a limit to which many of these things don't work in practice because you cannot monitorize, or people don't want to.
More thinking of training.
Yes,
and
absolutely.
find way of helping.
Absolutely. Yeah. Even I guess issues like dyslexia also show up in your reading scores and things like this, right? I don't know if there is an immediate translation, but I'm sure there are. And one could perhaps give little cues. Let's say someone has certain pattern of, maybe there's a certain pattern of eye movements that actually helps you grasp something better. I'm not sure what it would be in drumming, perhaps looking at the drum in a certain way or not. I'm not sure, but maybe if you measure behavior and you actually find that certain error patterns are correlated with certain eye movement strategies, then you can try to cue them to correct for that, and maybe it automatically corrects for the motor pattern. But these are all the kinds of things where you have to look, or rather more precisely, you have to set up the structure so that somebody looks. You know what I mean? Like you kind of set up the structure where you're measuring these data and it's out there. And then someone who comes in fresh says, okay, I need something to do, and I'm going to look at this data, right? And they find something. This is more that unless you have the structure set up so that these kinds of things are being done, and then other people will if that makes sense. So no, absolutely, and that's where I think that there's a lot of possibilities. But and so there's a certain element of hypothesis driven work, right? And this loosely hypothesis driven, what I just described. Some element of it is fishing. So you kind of have to be careful not to be searching, hunting, and fishing all the time. But what I just described is within the ballpark, I would guess, of exploratory work. Yeah.
And then one thing which is really interesting is like, let's say you're practicing for a performance, and then the day before you close your eyes and you
Yeah.
envision yourself doing it, so you hear
Yep.
and you envision, you see yourself.
Yep.
And part of what I'm looking at on the neural, is it possible to track the activations of neurons for that?
Yeah.
Also all the sensory motor preparation,
Yeah.
initiation.
Yeah.
And how much of a difference is there between actually doing the task,
Yeah.
and imagine yourself doing the task?
Yeah. So yeah, go ahead. Yeah.
No, that's just
No. Imagery. Yes. No, that's right.
If yes, how much of those difference can we?
Yeah. So absolutely. So imagery and perception, that link, right? It's very deeply explored. There's research programs of people looking at it. There's a very closely similar thing, which is sleep after training, right? And your motor learning, how it improves during one night's sleep, and how you get better. And also, we have this open question of how learning happens. We simply don't really understand it. Some people go like this, and then you've got this one burst of aha, eureka, and you don't know what happened in between. Or someone takes a break and comes back, and suddenly they're able to play the piece, and you don't know what they were doing in between. And we simply don't understand learning curves, individual differences in learning curves. So there's people looking at all this, and yeah, I guess in Montreal there must be a lot of people, given the strength of human imaging here, looking at both things, visualization and imagery prior to performance, how much you should do, when you should do it, right? That is an important question there, and also how you learn. So blocks of learning, how they should be structured, how often you should learn, what is spacing, right? For memory tasks, we have a good idea because it's very easy to measure. I give you 100 words, see how many you remember. It's easily quantifiable, it's easily measurable. So for memory, spacing techniques have been done. That's why you have all these index cards when you're learning language words, telling you how often you should repeat, which words you should repeat. But when it comes to musical performance, because of the external constraints on how often you practice or when you learn, right, you cannot exactly call up your teacher at specific moments and time it. But perhaps there are nice blocks, gradations of when you should practice, how often you should practice, right? And tailor that to individual measurements. I mean, these are all totally open questions. And yeah, you're right. Making measurements of the brain and the body to guide this would be totally interesting. But it's being done. There's a strain of work.
Thank you. I think we are at the end of 1 hour.
Excellent.
Les, is there anything else?
Yeah.
No, nothing else. Right. So thank you
Thank
again.
you.
That
Yeah.
was really interesting, and I hope that lots of people are going back home and thinking about
Thanks a
how
lot.
could we collaborate
Yeah.
together.
Absolutely,
Thank
please.
you
And
very much.
you can just search my name and you'll find my email. So please write. Yeah.
Thank you.
Thanks a lot. Yeah.